Ipfs-Embed is an implementation of Ipfs in Rust, which we have developed. It is started by David Craven in 2020, and it was built by David and me specifically for the needs of the company Actix. So it is open source, and it has some Kubo interrupt, but it was not the primary design goal. So if you connect to Kubo, it might work, it might not. It has worked at some time for some cases, but not really. So it wasn't our goal, basically. And it is intended to be used for small private swarms. So it's not meant to be used in the global Ipfs, but in a small swarm of, let's say, up to 100 devices. And so it is used in production in factories in Germany. So due to that, there's a lot of bulletproofing in terms of peer handling and all kinds of things that you only can figure out if you are in production and things start breaking at 2 a.m. in the morning. Okay, so Actix is basically, you have a private swarm, a private Ipfs swarm, which connects in the factory, connects humans with a tablet in the hand, machines, and nodes in the data center, and each of them builds an event log, and you want to get the event log from each device on each other device, so you can then do something with the data. Like, you have the current state of the world, and then you can make decisions based on your view of the world, which is built from these events. Okay, so features. It has low and most notably bounded resource usage, in particular memory. This is running on small devices. The smallest we have is a Raspberry Pi with 500 meg. And yeah, you cannot exceed the memory. Then the thing stops and people will be very angry, so it's just not good. And the API is guided by the principles of local first development. So basically, you work from local data when offline. So you have to clearly know when you do an operation, whether it will be local or whether it will connect to the network. And you never rely on the network being available. So obviously, you have to rely on the network sometimes to get some data, but at least the application should always be in a usable state. You should at least be able to tell the user, your data is not there, sorry. But you should never get a spinner, basically. And it's soft real-time. What that means is that it should not block for a long time because there's some stuff depending on it. But we are not using it to actually control machines which could kill somebody, so it's not used in a safety-critical way. But it is used in a way where you really don't want breaks of more than half a second or whatever. Okay, so therefore the API might not be appropriate for cloud usage. It's just very special. So Actix is published for basically all platforms, Linux, Mac, Windows, and Android, and Linux on basically every ARM architecture there is, because there's quite a bit of variety in these machines. Okay, API. So this talk is not about the internals. That would be too long. I just want to talk about the API, because we did a few things different than Kubo. It is based on Rust IPFS and Rust P2P and sqlite. And other than that, let's just see what the API looks like. So this is probably the most controversial thing. I started with that. So we got local I/O. You've got some operations which are always strictly local. You know when you call these operations, you will never touch the network. And so they are strictly separate from the network operations. And they are blocking, boo. So people really look down to having blocking calls and say this is like 20th century tech. But I find it very practical to have blocking calls occasionally. So async is not without performance and not without mental overhead. And being sync, so no async calls, simplifies writing complex logic on top of these things. And yeah, I got another talk tomorrow about one of the things you build on top. And that means existing local data should be consistently fast. So if you want to get a block from local data, you will get the block or you will not get the block, but you'll have an answer in less than a millisecond, typically a microsecond. So just no point making this async. It's not like you're going to wait for a second or whatever. Yeah, my opinion is that's the only thing to do in an embedded use case. People might disagree, but anyway. So it might be different if you have a cloud deployment like we've seen with other use cases where you are deployed in the cloud and your storage is not local to your peer-to-peer node, then this obviously doesn't apply. But this is for this use case. So this is our API. The local API you can get, you can insert, you can check whether the block is there, and you can list all blocks that you have. That's it. And this is the mental cost of async. This is the method in Rust with lots and lots of lifetime parameters. And I mean, I've been doing Rust professionally since 2018, but even I have a hard time understanding things like this. So it's not to be ignored. And the perf cost is that whenever you have async in Rust and you have abstraction, you often have to box, and that means you have an allocation. Even if you have a very, very cheap operation, you need to hit the allocator, which is not good. Okay, and so in Rust, they have this catchphrase, abstraction without cost. And I say, in async Rust, abstraction is no longer without cost. So, and that's bad. I mean, but surely not everything can be sync. So there's an embedded database called Sled. I think they do it right. They have cheap local interactions, which are synchronous. And then they have a call called flush, which just basically writes the state of the database to disk. And that is async. And Ipfs-Embed follows this. So we got a bunch of operations which are sync, which you've just seen. And we got sync is async, fetch, flush, and are async. So we got things that take a long time and they involve a lot of stuff are async. Okay, and there are some very funny runs by SpaceJam, the developer of Sled, about Rust async, and also by Tomaka, the main developer of Rust B2B, about Rust async. So if you have some fun, you can read them later. It's quite hilarious. I agree with almost everything there. Okay, so now that was the controversial part out of the way. Now let's take a look at our API. Other than that, pinning. So we got basically, pinning is, in our case, is completely independent of whether you have a block or whether you don't have a block. So pinning just expresses something like, if I had this data, I would want to keep it. But it doesn't mean that you have to have it before you can pin it. You can say, I want to pin this hash, even though you don't have the data for the hash. I mean, why wouldn't you? You're just expressing, if I had Wikipedia, I would be cool with that. And that means, for example, you can pin Wikipedia, and then you look at all the pages, and then everything you ever looked at in Wikipedia will be on your disk, because you express the desire to keep it by pinning the root of Wikipedia before you even got it. And then all pins are recursive. We haven't found this to be a big deal. And you can still have a link to something big, and you don't need to have it all to pin it. You know, you can have a DAG where you don't have some stuff, and it's no problem. Now we got two different kinds of pins. You have to think about, if you build a DAG locally, you always build a DAG from the bottom up. That's the only way it works, because you cannot have the hash of the root before you build stuff. And if you sync something from somewhere else, you always build a DAG from the top down, because you're syncing the root, and then you're syncing all the way down. And kind of for these two use cases, we have two different mechanisms. So temp pins are basically, you use them while you yourself are building a DAG. And what you do is, they are incredibly cheap. You can consider them basically free. And they use a Rust or a C++ pattern called RAI, meaning that you create a temp pin, and then as soon as you go out of scope, the temp pin gets deleted, and the SID is free to be collected again. And the intention is to say, yep, GC, please leave me alone while I build this thing. So in our case, the GC is constantly running in the background, so if you build something and it takes, like, let's say 5 seconds, there's a decent chance that while you build it, it would be collected. So to prevent that, you have this temp pin mechanism. And now, basically, they are ephemeral, so when you restart your node, your temp pins are gone. You have to, but if you are interrupted in the middle of building a DAG, you probably want to start from scratch anyway. Okay. So, and this is quite easy to implement in our case, because the IPFS lives in the same process as the application. So if the application dies, also IPFS dies. which is, if you have them in 2 different processes, you have this whole microservices dilemma, and it's much more complex. So this is the API. You can create a temp pin, and then you can add a SID to the temp pin, and you can add as many SIDs to the temp pin as you want. And it is very cheap. And then the other thing we have named pins. They're called aliases, and you usually have a few. You might have just 1 named pin per application. And so what's a name in a named pin anyway? It is a blob. I'm not a believer in restricting things like that or to UTF-8. There's just no point. If you have something which you might want to put in a name, like a hash or, I don't know, some other information, it's just a blob. And these are obviously persistent, and these are the ones that determine which data really doesn't need to be collected. And this is what the API looks like. You say alias, and then you have a blob, and then an optional SID. If you want to pin something, you set it to some, your SID, and if you want to clear it, you set it to none. And this is an example. So you build something, you create a temp pin, then you build your stuff. Then once you're done building, you set an alias, and then you delete the temp pin, which you don't have to do it. It happens automatically once it gets out of scope. So this is a clean way to build a big thing locally. Now, until now, we've only talked about local operations. Everything I've talked about now is just local. You know, local first in the talk also. Now we're talking about the network. So what do we have in terms of network operations? We got fetch. That's exactly like get in Kubo. It gets from local or from the network, whichever comes first. Basically, it raises fetching from the store and getting from the network. And then we have something else which is called sync. And sync basically allows you to sync an entire DAG. You just say sync and give it a hash. And then what it does is it produces a stream of progress updates. And then once it's done, the stream is done, and you know that your data is local. So once you have finished your sync, you can then only use the local API. And yeah, also we've got gossip sub, publish, subscribe, and we've got broadcast. Broadcast is something to just send something to all your current peers, which is in a local scenario, it's quite helpful because those are the ones which you can easily reach without multiple hops. Okay, this is the blocks API. You got fetch, which is async, and sync, which returns an object, which is both a future and a stream. So you can either just .await it, which means you're waiting without progress, or you can treat it as a stream, and then you can get some nice progress update. And you can show that it's syncing. And now this is an example how you would sync. There's one important thing here. When you sync, you have to make sure that your data is safe from GC while you are syncing, because otherwise you might sync it, and then GC might kill it while you sync it. So what you do is you create a temp pin, and then you sync, and then once you're done with syncing, you have this, you switch it over to an alias, and then you delete the temp pin. So even for data which is currently synced, you have to protect it from GC. So, okay, let's then, yeah, this is the messaging API. It's nothing special. You can publish on PubSub, you can listen to PubSub, and you can broadcast. Broadcast is just sent to all the neighbors, basically. And now we get to the store. And the store, the most interesting thing that the store does is garbage collection. It's based on SQLite. I was going to use Sled, but this author of Sled advised against it. He said, if reliable is your primary constraint, use SQLite, Sled is better. So, well, I did that. And I'm currently working on a future store, which is a radix tree with a custom storage backend, where you might use a storage backend from SpaceJam, the author of Sled, or a very simple storage backend which would work in WASM, like using IndexB or whatever. But it's never going to be the primary because it sucks. You cannot, it's really hard to have something which works well both in WASM and on native. I tried hard, but I think this is a good compromise anyway. So GC. So it uses a recursive SQLite query to find out the live set, so the set of all things which are currently pinned, and it uses SQLite advanced features with recursive, and then basically drops all the blocks that it has determined that are orphaned, basically. And now the notable thing is it does a second thing incrementally, so your GC pauses are not that long. So this is the SQLite, by the way. It's the SQL. It's quite complex, but the great thing about this is that it is not that fast, but it is bulletproof because it's inside a single SQLite transaction, and it will just work. Don't worry about it. It's one less thing to worry about. Okay, so you can set multiple limits on the store. You can set GC time limits. You can set a target GC time. That is the maximum time, or the target time that GC is allowed to run. So you set that to 1 second. It means the GC will try to run only 1 second at a time. Of course, the GC might take longer than 1 second, but then the GC will have to split it up into multiple runs. And then you can get a problem where you are not really making progress, and to make sure that that doesn't happen, you can set a minimum amount of blocks to be GC'd per run. And if you don't have this minimum amount, you will exceed your time. That's to make sure that you always are collecting enough, basically. And okay, that's that. And then you got another thing, which is the limits of the store size. We got limits both on the size and on the number of blocks. The reason for that is if you have lots of small blocks, it doesn't matter how small they are, they will cause trouble. If you have Kubo configured with 10 gigs, and I just put in 10 gigs of small directories, I promise you it will fall over because it is just too much stuff. So you have to have limits both on the total size and on the number of blocks. It's like in a Unix file system where you have an inode limit or something like that. So limits do not apply to pinned data. They are only about the stuff which is cached. And the config is here. You can set these two values. Now caching concerns itself with the part that is not pinned. So if you have 10 gigs free in total and you have 1 gig pinned, then caching is how to allocate these remaining 9 gigs. And there you have a custom caching strategy. So you can have one which is built in, which is in-memory LRU. Basically, just whatever is there which has been accessed last gets kept in case of a GC. So example, you have a gateway which has a lot of files, and the files which have been last accessed are kept. Then the next one is you have a persistent LRU. And in that case, it's in a separate database because this database is not as important as the main database. If it breaks, no big deal. You just lose information who has accessed your stuff. It's just, who cares? And then you can even have custom strategies, like if you have Unix FS, you only keep directories, preferably, because they are more important to find the structure and so on. And depending on your application, you could come up with a different strategy, what to keep in case of caching. Is there some more here? Yeah, so this is the caching trait. Basically, it's just a bunch of methods which get called on every access, which allow you to keep track of what has happened, so you can figure out what to keep. And there are 2 default implementations, and you can also roll your own, basically. So peers, we do a bunch of things about peers. So if you run on restricted hardware, you really cannot afford to have 600 peers. Just a no-go. So you have to be very careful about which peers you keep. So if you exceed the limit of peers that you want to have, you need to figure out which peers to throw out and which peers to keep. So what you do is you have a kind of hierarchy of peer value. So for example, your bootstrap peer, you want to keep them forever, in our case. Because this is probably boxed somewhere in a cabinet, which you know is always going to be there. If it's not there for an hour, it doesn't matter. Once you get back into wireless LAN, it will be there. So you always keep the bootstrap peer. And then we got stuff like if you have manually connected peers, you want to keep them longer than others because somebody made an intentional, you said, I want to connect to this peer. So please keep this peer because I told you, you know. And then the next thing is MDNS peers. Remember, local first. MDNS peers come from your network environment. And so they are probably more valuable than something far away told you, because there's more likely that you will get them again at some point. And then, I mean, the exact details don't matter. The main thing is that you have to have some kind of logic, heuristic about which peers to keep. You cannot keep them all, so you have to do something. So we got some API questions. There's a bunch of things internal to Rust. So this use this, we have implemented this, and as soon as we had something that worked, we had to move on to the next level. So we couldn't spend a lot of time designing the perfect API. So we have a bunch of questions left, but I think we will be able to come up with something better at number 0 now, that we have time to focus on this. And one of the biggest things biggest questions I have is, how do you do an incomplete sync of a graph? How do you say, I want to sync, but I don't want to sync the entire DAG because it's giant, I want to sync only a certain subset. And there's a bunch of heuristics you could do to limit the depth, or use graph sync, or send a predicate over the wire, or anything basically, but we don't know how to do that yet. Okay, and that's basically it. I think